that all the time now. So, okay, what is Andrea doing here? And, you know, what's her, why does she spend so much time here? But actually, let me first tell you, so actually I am a professor of human-computer interaction and web development. That means it doesn't sound anything like math, right? But actually, I do have a diploma in math. I started out being a mathematician, then working in a company and so on, and actually then afterwards I did my PhD very late in life, and I specifically chose a topic, an area of research where I do not interfere with Michael, because that's really difficult if you are married to a senior researcher. And actually my very first talk at HICM, kind of our home conference, actually there I was a spelling error. So, okay, very nice. Okay, but anyway, I just would like to give you a very short impression before I actually started out on the eye tracking. That is, before I became a professor, actually with this professorship came an eye tracking lab, and then I started with eye tracking, but before I used other methods, like for example, repertory grid interviews. But still, because I do have a diploma in math, actually I was always close to math, but from a very different perspective, namely, how do people interact with mathematics? Okay, and that's actually why I'm here, because I'm interested in how do people interact with proof assistants, for example. And so I learned a lot of proof assistants. I had a look at many proof assistants, but just, you know, something like that. We did that, like mathematical user or search interfaces. And then we did some cluster analysis, and for example, we found out that basically math people are different from no math people, meaning mathematicians really need different interfaces for search than non-mathematicians. And basically that was, you know, also some kind of, yeah, nice result. So, for example, here, so mathematicians appreciate function over form, and probably that was why you were smiling. What is she doing here? You know, human-computer interaction is about form, isn't it? And so on. But anyway, it was quite interesting, and it was actually used in interfaces like Michael's estate system or Alea and so on. So it really has its value. But today I would like to talk about eye tracking. So I would like to give you a very short introduction to eye tracking, and then I go into my research topics or our research topics, because I do a lot with Michael as well. Let's just start there. So actually, I will show you eye tracking now, not in the mathematics field, but to motivate eye tracking, I use advertising, because it's very intuitive what you do. So for example, let's say you would like to create an ad for a car company, and an ad for the street. That is, on these big poster sessions, you have a picture and some messages, and you have to make sure that actually when people sitting in their cars passing that poster, this big board, then actually they need to get the message. And you can see here, Neu-Ulm is really in the center of all the car companies, so that's always a very good example. But you can see here this crazy woman with a hammer. And okay, what is this about? What does it have to do? What is its message? And here, this Audi, the brand, actually always wants to make car driving, and their car specifically, make it emotional. They even have a sound design, you might have heard it, the heartbeat, because they always want to push emotion into the connection to the customer. So, okay, we can see emotion here, but what does it have to do with the car? And actually, the idea is that you have to understand this small word there. It says jealousy. Okay, so actually, in Germany at least, car drivers are dominantly male, and maybe women are jealous of the car. And so, okay, they want to maybe ruin their competitor. Also, that's the idea. But it all hinges on the fact that this jealousy is being understood. And you can see that it is not a high contrast one. It's very hard to read. It's small, it's not high contrast. So that's actually what you can find out with an eye tracker. So, and we'll see in a moment how this is realized. So there are lots of different eye trackers. You already saw the very small one. And there are bigger ones which have higher accuracy, I already told you that. But there are also now this 3D eye trackers, so if you have HoloLens or so, you can also observe eye movement with the eye tracker. They are very lightweight ones which are very mobile. You can go around with the eye trackers and so on, but basically all of them have this this same principle there. Okay, so let's look at this ad again, and now the analysis tools come in. So, for example, if you now look at the visualization where people look the most, or actually the longest. This is a heat map, meaning that the red areas are looked at the most. And you can clearly see, okay, the woman is very interesting, but also the jealousy. So this ad clearly works. Okay, and so something like that you can actually find out. If you are not interested in the heat map, maybe sometimes it's really important to see in which order you look at things. And then this is a so-called gaze plot, and actually here you can see this is a picture. In a picture, people look in the center, start there, get an idea with their peripheral vision, and then they look at the most interesting. And here, obviously, at the beginning, jealousy seems to be interesting. And that's fine for this ad. So now, in general, what can you actually get from the eye tracker? So you know, or the system knows, not only how your eyes move, but actually where you are looking at. That's called point of gaze. Or you can also call that fixations. If you have a time threshold, then, you know, if you look over a certain threshold there, it's called fixations. You can look at the order of fixations. We have already seen an example for that. You can count the fixations. You can define areas on your product, and then you can analyze how long they were visited, whether they were visited at all, and so on. You can look at the blink rate by now. More information about pupil dilation. Actually, if you are really interested in a topic, you know, your pupils dilate, and people look into learning there, for example, or saccadic intrusions, and so on. So there are different metrics here. And actually, I just would like to see how this looks like. So we are using the iMotion software at the moment, and you get, let's start here. So, you know, the respondents, so the participants, looked 94% of the time at a certain area. You can look at how many times this specific area was revisited, fixation count, and so on, and that is all automatic. So it's very comfortable to use because the system already takes over a lot of the work. And if you were wondering about when I said, where people were looking, you can define for yourself so-called areas of interest, like for example here the purple one, and you get the results for these specific areas. So here we have blue, green, and purple, and you can see that then, just to give you an idea. Okay, and you are not limited to just posters, obviously not, so not only limited to still images. You can look at websites, but you can also, as products, you can look at formalization systems. You could use as, how people use Lean or Acta or Coq or so. But you can also use that on real life products. Like, for example, we did an experiment so I did it with the students of mine in the course, and we looked at a self-order terminal. And that was actually a brand new idea because it was a self-order terminal for a bakery. So you can imagine McDonald's, Burger Kings, and so on, that's already common. But if you do it in a bakery, you have a completely different target group. And how would they react to that? Okay, and so on. And so this is just, a screenshot. And when people stand in front of the self-order terminal, this was the average eye height, and you can see they are looking here. Okay, that's actually fine, but it says here, order now, but it has no interaction. Actually, here is the real manual advice, the command, okay? So, touch screen, start order. But many of the older people, elderly people, actually they stand in front of this self-order terminal and they didn't know what to do. And what's this telling you is actually they are looking here and not there. So this command is actually on the right. It shouldn't be down there. It should be in the average height of the people. Okay, otherwise it won't be seen. Now that was specifically interesting because the company was so proud that it had so wonderful pictures. Yeah. But, if they can't, users can't use it.
Maybe the people are just admiring the pictures.
Yes, exactly. And so, human-computer interaction is important. Okay, but anyway.
Sorry, can I ask you something about the picture? What are those, the tracking tags around the...
Okay, so basically, if you do it this way with a laptop in front of you, then your eyes will be or the system will be calibrated to your eyes because you don't move a lot. But if you stand in front of the self-order terminal, people move. And so this is actually for the system to just gather the data in correspondence to actually where they stand and where they look, to understand where they really look. Right. Okay, so now I said, okay, but my research focus is really on math, and so I had a look on how people interact with math expressions, or I started out with that. So for example, if you have such an equation system, just think about it, very easy, right? The formalizers probably think, okay, what is that? But actually it's quite complicated if you think about it. Just with this equation system, you already set up a task. That's not that obvious to everyone if you don't know, how these tasks are generated. Then you have variables, you have operators, you have literals. And actually, if you have to understand that equation system, it's quite a lot of information to decode. Okay, and then you can ask yourself, okay, so how do people, or what is the category of this kind of information? Is it text? Is it read like text? That was something we were interested in. Okay, just to make sure that you understand what I'm showing you now. So, for example, if you look at such a nice inequality, then you could create gaze plots. So the order of fixations of people, every color is one participant, and you can see exactly where they are looking at what time, in which order. Then you can use heat maps, and you could use spotlight maps. So for example, with this equation system, where you can only see what they are really perceiving. Okay. Okay, and obviously some statistical data like the fixation metrics, visit metrics, and so on. Okay, now 2 ideas here. Math expressions are really a mathematician's pride, and actually you all have probably used math expressions, and they are 2-dimensional. They are not like text typically, they are not one line, but they always break the lines. So to speak, an integral is bigger, right? And that way, this 2-dimensionality allows actually the math expressions to contain lots and lots of information, really more information than text. Okay, and equation systems obviously are 2-dimensional. So you can ask the question, okay, not only is it being read as text, or maybe the variant is, it is being read like an image. Remember, an image, you start at the middle, and then you use your peripheral vision to spot the information, the important information. Okay, and here's a typical gaze plot by one participant for this very complicated math expression, or very complex math expression. So you start, then you look at it, okay, and actually the next thing is in the next, so in time-wise, the next fixation starts here then, and you read, okay, I didn't understand, I start again on the left-hand side and go right. And you can see, okay, that's like being read as text. You start on the left, you go right, you don't understand, you have to read the sentence again. You don't understand, and so on and so on. But is that really the case for, for all people? Just scanning the math expression and then actually, whenever you did not understand something, start again on the left-hand side? And the actually for us surprising result was this behavior is seen for all, or was seen for all our participants who said they are not math-oriented, they are not math-affine. They don't read the math expressions correctly. So let's look at a math-oriented person. And you can see here, wow, the right-hand side is not interesting to them. They start on the left, but actually then they basically go into the left-hand part of this inequality and deconstruct the math expression. And that was actually, we thought, really, really interesting. And obviously it was also not like an image, because then we would have started somewhere here in the middle. So actually what we found was that you need actually to learn a visual pattern for understanding math expressions. And that actually, that was new to us. Let's look at the equation system here. And again, we differentiated the people who did not or were not math-oriented, And you can see they start out in the middle of the equation system, like an image. Then they look around that, and after that they turn to text reading. They start on the upper left-hand corner and read it line by line.
Then with the previous image of the equation and the inequalities, then why? I mean, here they did not start in the middle. They were, you would expect them to start in the middle, but then with this example, they do start in the middle.
Yeah, that's right. But actually, they have to understand this is a math expression. They have to understand, I need to use this specific visual pattern for inequality, for example. So therefore, they need to understand what they are looking at. So that's true. But they decided on the important part, then, that you only look on the left-hand side. But we'll go into that in a moment, a little bit deeper. Yes, please.
Did the mathematicians ever eventually start looking at the right-hand side, or did they
yes.
only look at that?
No. So once they have deconstructed the left-hand side and understood what it says, then the right-hand side becomes interesting. So we were here, right? Non-math-oriented people. But now, again, very interestingly, we found the math-oriented people, they started with the operators to understand what they were seeing there. Okay, and so first the equality sign, the plus sign, and then they discovered the rest. So a very clear difference between, or I should say something else, and that is we coined the term math literacy. You need to have math literacy to actually being able to decipher the math expression. So we found that right, but that was, the first result. Then actually we went a little bit further, and that is we looked at the exact decoding. And it turned out that here on the left, so if you look, if you compare those two, that actually the people followed they followed an operator tree with function applications, where the function always is on the left-hand side, and then to the right, actually, each of the children are the arguments for the function, and also a special case were the beta bindings, so bound variables and so on. Okay, so let's have a look at that.
So you're saying we should write everything in Lisp?
Actually, after I have shown you how this one participant looked, it turns out that MathML has really the correct decoding possibilities and potential for reading math expressions. So we were 2 days ago in Marburg, and they are big on developing tools for blind people. And they were stunned with MathML, because MathML really gives them the opportunity to understand the visual pattern, but in a red, they read with a screen reader, it was red, and it was the right format. And to really decode the expression.
So the blind people read like a stack machine?
Everybody reads with a stack machine.
Yeah, exactly. But
you don't have to write it as Lisp. People read it as Lisp anyway. to stay in Mario's.
Yeah. So, for example, here this participant, he started with a beta binding, and that is because actually it is rather in the middle of the complete expression. Okay, and then actually understanding, okay, this is the formula, the participant actually understood what the general setup of the math expression was. Then the participant understood, okay, this on the left-hand part now, this has two parts, and the next he decided on going deeper in one branch there. And so here again you have three different parts, and I just try to do the coloring here. And once that was understood, he decoded further. An integral, right? Okay, so integral, that was being looked at, and actually specifically the lower bound. We couldn't find out actually why it was the lower bound, but obviously that was an interesting math expression there, let's say.
Because it comes first, right?
Yeah, maybe, but actually it's not usual that or it's not self-evident why you start at the lower bound and not
Well,
at
it's
the
not
upper
zero.
bound.
It's something interesting. There's something there, and it's not zero.
Yeah, maybe. Yeah,
I don't know how much intuition is useful in that situation, but for me, like, it's intuitive to you're integrating from left to right. The lower bound is on the left, so you think of it like.
yeah.
But it's also larger than the eta, which
yes.
wasn't looked at.
Yes.
The eta doesn't have any structure. The delta does.
So what does the at sign mean? Is that like
That's application, function application. So that you have a function, and the function you can. So, for example, here the function is the times, and here times, and then you have the one factor is C1 and so on.
Isn't there some algorithmic bias coming in because you showed the linear equations first? And how we learn to solve the linear equation is like we first see the first equation, then see, and similarly for the integrals, we know how we algorithmically learn to solve the integrals. We first see the lower bound and then upper bound. Isn't that kind of thing is affecting this?
Yeah, it might also be the reason, and it could well be. But the whole point here is that actually what we are being taught can be found in the visual pattern afterwards, right? And that's something, okay, if you tell that blind people, for example, then, no one says explicitly in a math expression, look first there, and then look there. But we know that. Somehow someone taught us, but not but implicitly, not explicitly.
when we read text, it is presented sequentially, but it's structured as a tree. But do people travel the tree like in any sense when they're reading text, or
So if they don't understand something, they jump back. Yeah, that's true, and that's helpful. But typically, if you read a book, Jane Austen, like for example, then you understand every sentence and you just
They're only the timings of the words are actually give you hints of what's going on cognitively. Whereas here, the order of things gives you hints on what goes on cognitively.
Do you jump to the ends of all the German sentences to find out?
No, we have stacks actually. And experimentally larger stacks than speakers of English.
Well, do languages have different patterns, reading patterns?
don't know.
Okay.
They might not have a
That's
strong
an
enough visual
interesting
signal
question.
to make it easy to do that, even if it was possible.
That's been very much studied by cognitive linguists.
Yeah. So actually, we can go through this, but it's actually really interesting because it is the depth-first traversal of the operator tree, and that was not that clear before. And actually, this let's say compositional approach is actually a math practice. And that was not clear beforehand. So then we asked ourselves, what about the scope of this math literacy? Is it just stuck to math expressions? Or if you have a text with math interspersed, then what happens then? And actually we did yet another experiment. So we gave a set of students this one-page information. Note it has math expressions in there, it has a background stating the background, it has a problem statement, and then some facts about it, and it has given the solution. And actually, they were asked to study that information and asked to write a summary afterwards. And actually, by asking them to write a summary, we could find out whether they understood what they had looked at or not. Okay, so we could make this differentiation again between low-level understanding and high-level understanding, but actually this text, they had worked with that text a couple of, I would say, months before, everyone in that class. Okay, and now let's just look at the gaze plot for this area. And what you can see there is that if you have math expressions, you always, or a lot of times, the people really jump back, make so-called regressions to really understand, to connect all the information from being data to information to knowledge and so on, this knowledge graph. So that was really interesting, and we just found interesting other patterns for how people visually understand such a text. Okay, then we wanted to understand, okay, so what about math literacy and math competency? Does that now connect? And we looked with the same experiment, we looked at that. And this is just the solution. We defined special areas of interest. You can see we wanted to understand how often, how long did they look at the equation 1, at the equation, or equation and system, I should say, 2, 3, and we actually made it even more detailed. Actually, in reality, it looked like this. So lots of different areas of interest, and what we found, on a side note, very interesting, is we have these empty spots there, and actually people looked there quite a lot if they wanted to somehow, or that was our interpretation, when they wanted to deeply understand what they had read. So the wide or the empty space is really important cognitively for resting and processing the information. Okay, but that's just a side note. Okay, so then, for example, let's just look at the left-hand side. You can see here the different areas, and just look at the blue and the green. And the blue indicates here, for example, the visit duration, how long did they visit this area, the good students and the not so good students. And what is quite obvious is that the time they spend is almost the same. It's not that the better students are much faster. Okay, so that was interesting, and so let's not go into that. But for example, if we now look at how often did they visit this area, and there you can actually see quite a difference. So just look at the blue and orange now. The third one we just ignore for the moment. And there is a real difference. Okay, so what we can draw from that, conclude from that, is the better students are much more active in their reading. They use so they move their eyes much faster. Okay, because they make this jumps, I understand this, I connect this here. And you can look at how often they visit the areas, but you can also look at the fixation counts. How often do they look there? Not only visit the area, but actually at specific spots there, and there the difference is even bigger. Okay, so they are much more precise. They are not entering just the area of interest, but they are on the spot, typically, visually. Yeah.
So, are you saying that then, let's say the low students, that they look just longer at a specific spot as opposed to jumping around?
Actually, they try to understand by just staring. I mean, it's frustrating because they don't know the visual pattern, how you should look at the text and find the right spots in the text. Okay. Yeah, let's actually go a little bit further. Then, yet another question. So we discovered more and more questions there. So, for example, is the pattern, is it a general pattern, or does every community of practice, that's a sociological term, actually, do they have their own patterns? Do they learn how to do that in their community? And for that, we had a quite interesting experiment. For example, here we used a formula of a Kicken paper in type theory by Bill Farmer. So just another math expression, right? And actually, we asked them, okay, so this is the one they knew. So all the Kicken participants had heard this talk, at least in theory, okay? And then we asked them, okay, we showed them this without the heat map stuff in there, and we asked them, is there an error in that formula?
With the boxes?
Well, so here, actually, we included this error. See, there's an epsilon and there's an alpha, and all the other stuff, we just left out. Black boxes or white boxes, I should say. And you can see that people looked at the white boxes. They were still looking exactly on the spot where they wanted to retrieve the information. But what's interesting here is that, okay, we differentiated between computer science people, the type theorists, you, and mathematicians. Okay, and then we looked at the heat map. Okay,
So they were all participants of Kicken, right?
Yes. Exactly. And we asked them whether they consider themselves more mathematicians or type theorists, basically. Okay, so we couldn't conclude anything. Okay, but then we actually looked at whether they were right, how right their answer was, how correct their answer was.
So you're putting in all these boxes in the formula.
Yes.
And you're asking, I mean, this is a really hard question. Like after you like erased all of the meaning conveying parts of the formula when you do this.
That's true, but you have to understand what is meaningful then.
Well,
I mean,
it's just a type error.
Well,
What the F's and A's?
I'm saying without knowing its app, it's not even clear that there is a type error, right? Because what is this even applying to?
It's not a type checking exercise. It's like your intuition should tell you see that pattern over there, the alpha to epsilon, like you would expect it to be.
Did you tell them that they've seen this formula before?
No, we didn't want to embarrass them.
So they did know that they'd seen this formula before, but what was the question that you asked them?
So actually here we ask, is this a faithful representation of the given formula? So actually I think we had shown them the formula before.
Yes.
Okay, so they didn't know what they're typing paragraphs.
Yeah.
Okay.
Sorry. Right. But now you have seen CS and math differentiation was not some kind of different separation, but actually now we are just looking for the math people, just math people, and the ones who said there is an error,
No.
and people who said there is no error.
The other way
The
around.
other way.
Ah, yeah. Okay, and so you can see clearly that actually you can conclude the answer from the heat map here. They knew what they were looking for. Now, this might be interesting or not. It's 50-50, right? So it's maybe not that concluding. But actually for the CS people, time theorists, that was, we thought, really interesting because, 75% directly, they had looked at the important information in this math expression, and therefore they recognized what was, what was important, and they memorized what was important there. And you can see again the difference here in the heat map. Okay, so now should we go into that or not? But what's interesting, so we can actually see the heat map shows us about math competency. Okay, or actually, maybe we started out with math competency, and then we can see a different heat map or visual pattern. But the question is, can we turn that around? Can we deduce from the visual, from the visual pattern, can we deduce competency? That would be interesting.
Well, it's
Right.
correlated, right?
Yeah, but not more. So, but that would be really great, because if we could observe people, then we don't have to write exams, let them write exams any longer. We just observe their visual pattern and then pass, fail. Yes.
If you point them where they should be looking, do they do better on the questions?
We haven't done an experiment on that yet.
You should team up with Andrea.
This is just that image pattern that we're seeing is causation from the math competency, or?
So we can't do that. I mean, we observe that and then we differentiate it between the competency.
Yes, sir. Right now it's just establishing the correlation, right?
Yeah, exactly.
It's not enough to
No, not yet. No. But actually, right now, when we were in India, we did another experiment, and we are still in the analysis phase, whether we can actually now see, or conclude from the pattern to the understanding, what kind of understanding there is.
Well,
We don't know yet.
In the previous example, you could do that. Right? You can almost certainly, all of the people that said yes, we're looking at the right spot. So if you took a random person, you could guess.
Well, you would need Bayes' rule to turn around the direction, and you would have to have the right priors and all of those kind of things. So there's a little bit more to do, and whether it actually works, we haven't looked at. But right now, it's more there are interesting phenomena, and then we'll see it later.
Most of the people who said there was an error looked at the error.
Yes.
They looked there.
Sounds plausible.
Those who said there wasn't an error were sort of
What's surprising is that people that didn't find the error weren't looking at the error.
That's not surprising either.
Well, because
It's fine.
you might imagine that they looked at the error, but they don't identify it, but that's not the case. Again.
Yeah. Yeah.
Like when
Say we
I'm
have
looking for
great
something
answers yet, but actually we have interesting observations. Okay. And actually, now we know more about math, and actually that's why I included now the next slides, because you can really apply that then in systems. And if I were to find out something about formalized mathematics or formalizing math, then it might have consequences for the tools themselves, and that's just what I would like to show you. So, for example, Michael's flexiformalization or S-test and so on, if you look at it, it really enables you to decode, right, stuff. And that's actually what he made use of then in his Alea system. I think Alea was shown to most of you by Michael already. So, for example, in the Alea system, for example, you have these blue terms and the magenta terms, and the blue terms are references to definitions. And if you hover over such a blue term, you get, for example, the definition of what the strategy is. And here you can also see, okay, or what an optimal strategy is. And the magenta is actually the term which is defined in that statement. Okay, and let's say you hover over strategy, then you would decode the information, and that's actually what people do by themselves. But it can be very helpful if they do not understand that you decode the information for them. That's, just a consequence then. In Alea, you can actually also click on the magenta terms of this so-called definienda, and then you get other interaction opportunities, like, for example, the guided tours. So if you look at the definition of a term, that is based on the shoulders of other definitions, right? And this is done in the guided tour. So, for example, for optimal, you need to know strategy, need all the kind of concepts which are defined before. And you can just support this kind of decoding. But look here, because, yeah, this is the scroll bar for the guided tour. Lots and lots of concepts, and actually that would not be feasible at all in Andrea if you didn't have a learner model, because if you have a learner model, if you know for a concept whether this learner already knows about it or not, then you can make it visible or invisible. Okay, so here all my things are red, my learner model is still red, I need to learn everything. And so then the guided tour is really long. But if I had studied faithfully from the beginning, then actually this would be more. You could handle it.
Why isn't, now it's already the strategy, the optimal one, this is like, I don't know, say the end result in a way. Why don't you start with the definition? I mean, I find it strange. Like to go top down if you want.
Yeah, but actually, if you click on the guided tour for optimal, do you want to really start? I mean, it has nothing to do with optimal if you start at the beginning of all the concepts. So you would have to know what a set is, what, the very basic concepts. But actually, they do that, obviously. I mean, I'm here at the end, just to make sure that you get the right relationship there. But in Alea itself, you know, you get the most basic definition at the beginning. But because these are so many, or potentially many, actually the connection is not being made. So I used Alea as a test system for my students. And they are not math-oriented, but anyway, they really did not get this guided tour. Not at all. It was really frustrating for my client. Okay.
Well, just need to figure out the market. You are saying that like mathematics-oriented people read differently, so perhaps I'm sure we interact differently with these kinds of systems than non-math people.
That's true, but if that is the project in your course, we talked about Alea all the time, and they were asked to suggest improvements and so on. They really thought about that deeply, but they didn't get it. Yeah.
They didn't get what exactly? They didn't understand how to improve it, or they didn't understand what it was for?
They didn't understand what it was for. They were, I mean, they are partly design students, and they couldn't believe this visualization of the learner model. Let's say, and the interaction there. But anyway, that's just on the side note. But what I wanted to point out here is, in the Alea system, for each concept, actually, you manually have to determine whether you understood the concept or you can just remember the concept. For each single one. That's such a lot of work. I would say it is, yeah, if you don't have quizzes and so on every single concept, then it's not feasible. And so the idea that actually you can conclude from their eye movement some understanding, that would be so helpful. And that's why we set up this experiment now.
And I have a sort of random suggestion here regarding like how you can get more information out of this. You could start by showing the final thing, like the strategy, optimal strategy or whatever, and then people click on the links to see more, and then you use that information of what links they're clicking on to figure out sort of what area they know, and use that to infer sort of what other things might they know or not know. But
people give up before the 97 levels they have to go down to reach something they already understand. It's kind of backwards. If you recursively click on the do the hovering, that works, and that would indeed give us that information. But people give up.
Going from the top down, you understand. You'll understand the concept, but you will not be motivated to understand them. Right? You'll like, oh yes, there's something far in the future that I'll care about, but
yeah, the guided tours as they are now, with an empty learner model, are brutal. Yeah, I think they're forbidden by the Geneva Convention, or should be.
Could you use like a kind of binary search, like you show a easy concept, show a hard concept, then you like go.
Yeah, so
to bootstrap the model.
We do all kinds of bootstrapping of the models. Kind of ask for past grades and use that to bootstrap the model. And actually ask them, you should pay attention in this course from the first day and build up your learner model, then life is better for you. You're probably not shocked if I tell you that not all students do that, even if I tell them to.
Well,
but let's...
Yeah, I mean, just look at all the I mean, you are not aware how huge your knowledge really is before you look at something like that. Okay. What I wanted to show you was that if you have formalized it in that way, in the flexiformal way, like for example here you have the definition of a topology. I just would like to spread some ideas here. So then, for example, you know that the term topology depends on other concepts. And you have seen that with the guided tour. And actually, then we can interpret that as a terminologically dependency order. And, you know, maybe you have something like this. And then, you know, the card game, solitaire game, that only depends on a dependency order. And if you have that, you know, gamify it. Like, for example, this way. You start with topology, you have cards here. Okay, and then you have to move the concept, whether it is above or besides or below in the graph. Or then you have n. Then maybe you have finite, but finite might be in between. And so, right? It's just, you know, plain, obviously. Okay, just... then you can play with what kind of formalized knowledge you basically have, and then you can create services based on that. I'm not really going into that. This is a failed experiment. We thought, okay, it would be great to find out about math expressions, how the line breaks should be, specifically on the small smartphones, right?
That's not scientific.
But you know, we tried this out, and actually we did the experiment, and we just used very, let's say, consequently different line breaking rules. And it turned out we used math expressions which were simply overloading our participants. And so they looked everywhere, they thought so it was not analyzable. And so that was a failed one. But that, you know, there are lots of opportunities for eye tracking, and maybe if you now have a good idea what you can do with the lean coq actor PBS and so on, and an approach or so, then, you know, contact me and maybe we can set up an experiment. Maybe I will use you for this Indian experiment, yet therefore I didn't include it here, because maybe you can be my participants here as experts in that knowledge. Okay, so that's it. Maybe let's show that. So, do you have questions? It's a very foreign topic, right?
In the previous slide with the one before here with this one.
Yeah.
To be honest, for me, this is also like abstract nonsense. Let's say when I look at this, this is also so. It doesn't. I think I understand the idea.
So actually, the task was okay. Tell us whether that is a correct simplification.
Oh, okay. Yeah, this was unconditional.
Yeah. So we set up the experiment with a nice task and so on, but we took care that actually all the terms will vanish, you know, and so on. So it was supposedly easy, but
yeah, but it's funny, right? I see a wall of formulas like that, even like reading my paper. My first instinct is to skip.
Yeah.
Eventually, you have to come back in the paper.
When I need it, I'll go back because I'll have a.
Maybe I'll have a better form factor next time.
So actually, our next question was: do people really look at math expressions on their phones? This kind of math expressions.
Yes.
Yeah.
It depends on the age.
Maybe we should.
I never do.
We enliven that experiment with such participants.
Yes. The problem is, for everybody, in these experiments, you basically have to set a task that kind of hides the actual thing we're looking for from the participants. We didn't tell them that we were looking for line breaks. So you have to let them do something. And if the task the foreground task you have to give them, and what we didn't realize was that in all of these things, we basically asked them, basically look at this at point 0 or something like this and see whether, and essentially the bracketing was wrong, so that you needed you needed to remember too many of the intermediate values. We would have, instead of doing it kind of in a right bracketed way, have done it in a left bracketed way that you can profit earlier, then it might have worked. But this was just a misdesigned experiment. And it's easy to do that.
Another thing I was thinking is that it seems a bit sort of synthetic. This example, like if you have an example which is sort of motivated by, within the context of a proof or something where, it makes sense that this would come up, I think the context of that will help with like understanding where to look.
A question like, is this proof correct? Which has a formula in the middle. But I would say one thing, I do look at maths in my phone, and sometimes I just open a paper, but that's rare. The most common thing is like when I'm talking to someone about math and I want to share, and doing that by WhatsApp, it's kind of painful. You have to like mix, put the latter. It's painful, but I mean, do it.
Maybe it's worthwhile.
I also wanted to give an example from Mikhail's talk yesterday about regarding the guided tour thing, and like I think Mikhail, like it was essentially the problem of like, okay, here's a really complicated definition. How do I break it down into pieces and explain it? And one of the things that came to my mind is like, well, it's not really guided tour in the sense of like, we'll start from the axioms and work our way up because we'll never get done. I think there's a great degree of like, well, you just cut things off at a certain point. You say, this is a black box. We'll not think about it right now, but like explore other aspects of it. And I think that's missing from the guided tour approach.
Yes, I completely agree. One of the results we have, guided tours work well if you have a very well curated learner model. But if it's empty, they're horrible.
But
then you don't do some other barriers.
Yeah, it's like even if I don't know the thing and I'm not expected to know it, it's just like I know that if I explore that subtree, we're gonna be here forever, right? So
but that's why you need like good design for your system so that you have like natural interfaces, barriers where you can cut it off and say like, this is all a black box, you only need to know this couple of facts.
But now I'm interested in this one. And, blend out everything else.
Yeah.
Yeah, I mean, the sorry is a very simple way of doing that. But can you actually recover a sorry? So that you have parts of it, but you can hide parts of proofs?
Well, so, I mean, sorry is usually used for like when you're in the middle of a development and you'll have only half of a proof. Or you might sorry a definition in like really big, definitions. Maybe it's just too much stuff and you're just focusing on the types of the definitions or something and you want to ignore it. It's usually not used so much for just like a learner, like this is already a completed proof, but I will deliberately sorry out pieces of it for teaching purposes. I guess I've seen it done that way for solutions, if you assign a problem, you might write the solutions first and then sorry them out and give that to the students.
But the sorry out process is manual.
Yeah.
Or can you click the button and say, okay, sorry it out, re-sorry it into real life?
Oh, the meta math system, it has something a little bit like this.
Okay.
When you prove, you have to prove like every single little thing all the time, and it has kind of a mechanism for detecting which steps are meaningful and which are not. It's very primitive. It's just about like kind of whether it is an application of something or just syntax. But it does offer you a way of like showing you just the summary of a proof, which is interesting. Maybe Mario can explain better the thing.
You could observe your subjects also in other ways, like taking brain.
Yeah, but that's really intrusive.
You could then follow what they do with their mouse on a screen, things like that. So how would you locate your method, or this eye tracking, within the other possibilities of observing?
So it's a different kind of observation. I mean, what I wanted, or maybe what I can show you, is that we also have in the system, we do have an emotion tracker.
Ooh.
And actually, that is also
It's just anger.
How can you track emotions?
The face and the expression.
Looking at facial expression.
But wait, how? Like people with the autistic spectrum probably have like muted expressions, and mathematicians have a higher incidence of the autism. Does that pose a challenge in emotional track? Like,
Absolutely. There are also some people who have a non-working webcam. And that is a really big challenge for tracking. So you're never going to get everybody.
Yeah. Nice. Surprise. Surprise and anger, yes.
How reliable is detecting emotions based on facial microexpressions?
depends whom you ask. So the eye motions people really think it is very good, but actually we have problems to find the threshold. Yeah, but
Oh, I do identify with this.
This list of
Not reading
actually
that.
it has Do you remember it?
No.
There was such a nice example. Actually, I think it was the other one. So I just have to find it.
And how accurate are the detectors, like on the scale of text? Because sometimes people are looking like over a bit above the text. Is it possible they were?
It depends on the calibration. So before you start such an experiment, actually the participant has to look at 9 dots on the screen, for example. And actually with a product, with the self-order terminal, they had to look at different points. And then the system analyzes where you are looking, you know, when you move your eyes this and that way. And if it's a good calibration, then that is good.
We are eating into the cake break, and so I guess Andrea will be around. You can corner her near an eye tracker, and then by then she's found the nice example.
Actually, this is a nice example I wanted to show you. This is another of these car ads. And, you know, the problem is, does the message come across? And the thing is, you have feathers and tar, and actually Audi is very proud that actually the car stays like feathers on tar to the road. Yeah, very, very. This didn't come through, right? Because it didn't work. But what you can see here is that so, for example, here you have a surprise and you have joy, and you can see actually that so if you look at very good example, then first there's joy. Ah, feathers are nice, very nice. And then they look at tar. Oh, what is that? And then at the end, actually, they are really getting angry. What is this about? I do not understand. And with an emotion analysis, actually, emotion tracker, you can find that out. And actually, it would be maybe also interesting, you know, when people are getting angry in a proof, right?
Often, if I am any indication.
Yeah, but
Self-hate.